Deep inside the Arctic Circle in northern Sweden sits the fractured wreckage of a Royal Air Force heavy bomber. This is an Avro Lancaster Mark I, serial number F920, nicknamed Easy Elsie. In 1944, it belonged to 617 Squadron and is associated in records with the squadron code KC-E and the service identity AJ-E. Today, it represents a unique preservation conflict. The primary threat to this airframe is not only harsh weather or local scavengers. It is the unresolved tension between a protected northern landscape, heritage law, land access, and a modern campaign to recover the surviving hardware before the site loses more physical evidence. A hard scrapping deadline has been reported by campaigners, but official Swedish heritage records currently describe the wreck as a possible ancient monument under review, not as a site already scheduled for demolition. We know the precise location of the aircraft. We know its operational origin. The physical evidence on the ground provides an unmistakable signature. Resting on a forward section of the severed fuselage, the original wartime nose art paint remains visible. The painted letters spelling Easy Elsie have survived direct Arctic exposure. This paint strongly supports the identification of the bomber, but it should not stand alone. The identity is strongest when the nose art is read together with wartime records, the crash location near Porjus, the 617 Squadron connection, and the known mission against the German battleship Tirpitz. The structural remains are consistent with one of the specialized aircraft dispatched for that attack. Despite this strong identity and deep historical significance, the site remains trapped in an unresolved institutional conflict, not a confirmed order of erasure. This uncertainty creates a rigid procedural conflict between preservationists and local land management. British aviation historians and recovery campaigners want to preserve what remains of the airframe and the engineering details still visible in it. Local authorities, meanwhile, must work inside Swedish land, environmental, and heritage law. If preservation groups fail to secure a lawful recovery or protection pathway, campaigners fear the wreck could eventually be removed or treated as waste material. But a confirmed official order to cut up and melt down the aircraft has not been established. The current state of the investigation relies strictly on non-intrusive surface surveys. Investigators have mapped the perimeter of the debris field. They have verified the presence of the nose art and specific structural modifications. Jurisdiction remains tangled. The aircraft was a British military machine, and British guidance treats recovered parts from crashed British aircraft as Crown property unless ownership is formally transferred. But any physical work still has to pass through Swedish authority on the ground. The unresolved management question changes how aviation archaeologists approach the site. A normal survey would support long-term in situ preservation, leaving the wreckage undisturbed for future study. Here, campaigners argue that the physical record may have to be documented with recovery in mind, because protection, access, and clearance outcomes remain unsettled. This paradigm shift introduces significant logistical constraints. The preservation teams must secure funding, design an extraction plan, and negotiate access rights through the very same bureaucratic channels that ordered the destruction of the site. They are not fighting the natural decay of the bog. They are fighting a ticking legal clock. Every month that passes brings the 2026 deadline closer. The evidence discipline required here is strict. Investigators can verify the nose art and visible structural modifications, but they cannot guarantee that any lawful recovery plan will be approved in time. For that reason, every exposed feature has to be recorded now. Paint, metal dimensions, fragment orientation, and the visible relationships between the surviving structural chunks. The preservationists are racing against a rigid institutional process that lacks any mechanism to evaluate historical value. What precise cascade of mechanical failures forced a strategic bomber to land perfectly intact in a remote, neutral marsh in the first place? A strategic bomber damaged over a target faces a harsh trade-off between distance and aerodynamics. For this operation, the aircraft had to complete an approximate 2,250-mile round trip from Scotland to Norway. This flight path pushed the absolute range limits of the airframe. It required strict fuel management, precise navigation, and ideal cruising speeds. When intense anti-aircraft fire disabled vital mechanical systems over the target, the flight crew lost the aerodynamic efficiency required to cover the remaining distance. The operational constraints defining this flight began long before the aircraft encountered ground fire. This specific bomber was specially modified to carry a 12,000-pound payload known as the Tallboy. Standard bomber configurations could not accommodate a weapon of this enormous size and mass. To make the lift possible, engineers removed the mid-upper defensive turret and stripped heavy armor plating from the fuselage to reduce empty weight. They installed heavy-duty specialized suspension gear inside the bomb bay to secure the oversized weapon. Furthermore, to fully enclose the bomb, the standard flat bomb bay doors were replaced with enlarged bulge doors. These structural changes shifted the center of gravity and increased the baseline aerodynamic drag of the aircraft. The airframe was optimized strictly for heavy lift capability, trading away speed and clean airflow. Over the target zone and on the return leg, the bomber took damaging anti-aircraft fire. One engine was hit over the target, and another engine was later knocked out as the crew tried to get home, cutting the available thrust to 2 engines. The same damage also knocked out the hydraulic system, and accounts report damage to the radio equipment. The loss of hydraulic fluid pressure triggered an uncontrollable aerodynamic crisis. Without hydraulic locks holding them in place, the heavy main landing gear assemblies dropped down into the slipstream. The large, bulged bomb bay doors also fell fully open beneath the fuselage. The loss of 2 engines created an asymmetric and drag-heavy aircraft, forcing the pilot to fight the machine constantly as the landing gear and bomb doors hung in the slipstream. To counter this severe yaw, the pilot had to apply maximum opposite rudder deflection. This constant flight control input, combined with the deployed landing gear and the open bomb doors, generated massive parasitic drag. The aircraft required maximum continuous power from the 2 surviving engines just to maintain forward flight. This high power setting rapidly burned through the remaining fuel. The extreme drag profile prevented the aircraft from maintaining level flight, forcing a steady, continuous loss of altitude. The crew crossed an irreversible threshold. The aircraft could no longer trade power for distance fast enough to reach Scotland. The pilot, Daniel William Carey, had to evaluate the remaining operational limits. Ditching the heavy aircraft in the freezing Norwegian water without a working radio offered a 0% margin for rescue. Carey chose the only option that extended their survival window. He diverted the crippled bomber east. He carefully traded his remaining altitude for distance, clearing the jagged Scandinavian mountain ranges to penetrate neutral Swedish airspace. Once clear of the high terrain, the aircraft required a flat expanse before the fuel tanks ran dry. Carey located a remote peat bog near Porjus and made a forced wheels down, landing on the marsh. The ground offered no runway, no road access, and no realistic way to fly the bomber out again. The impact was hard, and accounts differ on the injuries. All of the crew survived. Carey is reported to have injured his knee, while other summaries mention minor injuries among the crew. They were subsequently interned by Swedish authorities and later repatriated. The forced landing left enough of the central structure recognizable for later investigators and visitors to identify the aircraft and its rare wartime modifications. But the site should not be described as a clean, intact slide preserved by mud alone. After the crew survived, the aircraft was reportedly set on fire, later stripped of useful items, and then cut up by salvagers. How did this terrain preserve enough evidence to matter, while dooming the modified airframe to permanent capture? The physical boundary of the remote Arctic bog terrain strictly limits the deployment of standard recovery logistics. Survey teams attempting to document the site are blocked from bringing in cranes, heavy trucks, or tracked transport vehicles. The soft peat marshland simply cannot support heavy weight. There are no solid access roads cut through the surrounding dense forest. This geographic isolation forces investigators to rely on a strict, low-footprint pedestrian methodology. They must document an 81-year-old debris field entirely on foot, carrying all necessary mapping equipment on their backs. The bog helped preserve enough structure to matter, but it did not preserve a clean crash pattern. The forced landing and later human interference left investigators with a damaged, partly artificial scatter. Therefore, the primary objective for the modern survey team is not merely finding the aircraft, but reconstructing a heavily altered and artificial scatter pattern. The investigators must build a comprehensive perimeter map to lock down the current spatial distribution of the structure. They must carefully differentiate between the original deceleration path carved into the bog and the subsequent artificial dispersal caused by the salvagers. Within those limits, investigators would work from fixed reference points, walk the site carefully, plot visible fragments, and photograph each exposed section with scale references. Where conditions and permissions allow, overlapping images could support photogrammetric models of the visible debris field, while the public Swedish record remains only a baseline listing, not proof of a full intrusive engineering survey. Operating in this environment demands strict discipline and constant risk assessment. The ground itself is a persistent hazard. The surface of the bog consists of floating vegetation mats covering deep pockets of freezing water. Surveyors must probe the mud ahead of every step to avoid breaking through the crust. The physical exhaustion of moving through deep peat while carrying camera bodies, heavy batteries, and safety gear strictly limits the amount of time the team can spend actively measuring the debris on any given day. That record fixes the wreck as a visible aircraft scatter within an area of roughly 30 by 40 meters, but it does not provide the exact dimensional relationships needed for recovery planning. That higher level of precision would require a dedicated, permitted survey. With the scatter perimeter mapped, what unique hardware remains trapped inside the severed fuselage sections? Historical aviation archives are frequently incomplete, and surviving technical records do not always answer every question about field-level wartime modifications. Historians should be cautious about claiming that every relevant blueprint has vanished. What the Swedish wreck offers is something different, a rare physical source that can be compared against the paper record, filling gaps where the documents are silent or ambiguous. The survey team focuses its initial visual inspection on the most coherent surviving structures. In this chapter, the nose art functions less as a new identification claim than as a diagnostic shortcut. It confirms that the forward skin survived well enough to support visible, non-intrusive documentation before the analysis moves aft into the modified bomb bay. Moving aft from the nose art, investigators can focus on the specialized bomb bay, the section most likely to retain chapter-owned engineering evidence. The precise surviving geometry on NF920 would be valuable because it can be compared against known Lancaster and Tallboy records, not because all paper evidence is known to have disappeared. If coherent hardware remains inside this fuselage segment, it could allow modern investigators to document the payload adaptations directly. Careful photography, measurement, and recovery under permit could show how the airframe was reinforced and how the bomb bay hardware was arranged for the Tallboy load. That would be a major knowledge gain, but the public record does not yet prove that this internal hardware has been fully measured or reverse engineered. The site may still provide technical answers about the bomb bay configuration, but only careful permitted examination can determine how much of that evidence survives. However, the site also enforces a hard limit on forensic interpretation. The coherent evidence only extends through the center mass of the aircraft. The outer wing structures and the engine nacelles were heavily scavenged in the decades following the crash. Because the engines and their mounting structures are completely missing from the debris field, investigators cannot analyze the shrapnel strikes that initiated the loss of the aircraft. They cannot fully interpret the structural load path of the battle damage. Without the engines, the physical proof of the mechanical failure chain is lost forever. The coherent central sections perfectly prove the identity of the bomber and verify its rare engineering modifications. But while the forward structure remains coherent, what does the rest of the scavenged debris field fail to show? The wider debris field shifts the investigation away from clean impact reconstruction and toward interference analysis. Material removed after the crash, later cutting, displacement, and reported returns all blur the boundary between landing damage and later dismantling. The useful evidence now lies in the specific detachments. Surveyors locate segmented forward fuselage chunks out of alignment with the main impact trench, while fragmented bomb bay sections and isolated aluminum panels sit across the peat with no reliable structural relationship to their original aerodynamic positions. These detached pieces complicate any attempt to read the forced landing mechanically. Because the fuselage was cut into disparate chunks by individuals using hand tools, crude saw cuts and tearing actions overprint the original aerodynamic stress fractures. If a bulkhead is found cracked, the team cannot definitively prove whether the wet mud caused the fracture in 1944, or whether a local scrap hunter forced it apart decades later. Beyond human interference, the bog adds a conservation problem, not a simple countdown. Detached evidence has spent decades in wet peat, where aluminum, magnesium, steel fittings, fasteners, and damaged coatings can create localized corrosion risks. The severity depends on oxygen, acidity, salts, alloy type, coating condition, and burial depth, so the safe conclusion is narrower. Continued exposure may gradually erase measurable engineering detail. This ongoing decay means some physical evidence may be losing clarity at the edges. Detached bomb bay fragments could lose measurable detail through corrosion, distortion, abrasion, and handling damage. Once metal is badly corroded or broken, investigators may struggle to tell whether a missing section was torn away during the landing, removed by later salvagers, or degraded in the bog. The limitation is real, but it should be framed as uncertainty, not as a known countdown to total dissolution. The constraints of a non-intrusive survey mean investigators cannot lift or turn these detached pieces to inspect the unexposed surfaces. If a crucial engineering stamp or modification serial number rests face down in the mud, it remains completely unreadable. The survey team must accept these blind spots as a strict operational boundary. They can only document the exposed upper surfaces of the bomb bay fragments and the visible edges of the forward fuselage chunks. This procedural discipline ensures the site remains undisturbed, but it guarantees that a significant portion of the historical record remains inaccessible. The physical condition of the site dictates that no further definitive impact conclusions can be drawn without a full extraction. The survey record can still fix where visible fragments lie today and preserve the condition visible from the surface. Only repeated condition monitoring or material testing could show how quickly the remaining structural evidence is being lost. What human timetable now threatens to outrun that slower, uncertain decay? A preservation window now controls the way campaigners talk about the physical remains of this aircraft. Their urgency rests on the possibility that the wreck's future could be decided before a lawful recovery or protection route is secured. The current crisis is better described as a prolonged jurisdictional and access problem. Campaigners have described British permission or support for recovery in some form, but public official documents alone do not prove a complete authorization for physical work on Swedish land. The aircraft therefore remained in place, protected partly by isolation but caught between permission in principle and authority at the site. That administrative boundary has not been proven to have shifted into active destruction. The management risk is narrower but still serious. Unless a recovery or protection pathway is secured, campaigners fear the aircraft could be handled as unwanted non-native material rather than preserved as a historic wreck. This classification places the present management condition of the site in jeopardy without proving that active destruction has begun. British preservationists are trying to secure the remaining structure before administrative decisions, deterioration, or future clearance remove the chance for detailed study. Their strongest argument comes from the surface surveys. Visible nose art and rare bomb bay features show that the wreck still holds physical evidence worth protecting, even where the archive remains incomplete or ambiguous. Any controlled recovery would still face severe logistical constraints. Beyond funding and permissions, the team would have to lift fragile aluminum structures from deep mud, package them securely, and move them across roadless terrain while proving that the extraction itself would not cause further environmental damage. The site currently remains partially documented, establishing what visible proof still rests in the Swedish marsh. If no lawful pathway emerges, that record may become the final archive of the aircraft's surviving modifications rather than the first stage of its preservation.